Hey, geometry students, I'm going to walk you through. So the first one talks about a conjecture. And basically what I need you to know about a conjecture is that it's an unproven statement based on like patterns or observations. So it hasn't been proven yet, so unproven statement based on observations. So what you do with a conjecture is you need to test it. In order for you to kind of take it for to be true, like you have to kind of test it in a variety of scenarios to see if it kind of holds true throughout the entire, like for every kind of example. All right, so inductive reasoning is where you find a pattern. So first, you find a pattern. So you might notice something that's happening with some data, right? You might notice there's a pattern, and then you use that pattern to write a conjecture. So what you're noticing is kind of like what you're talking about here. We're kind of combining the two vocab words. So you're noticing a pattern, and what you're doing is you're saying, okay, I've looked at this pattern, I've seen it in a variety of scenarios, let me write a rule or a conjecture. So a conjecture is something that you haven't necessarily proved, but you've tested in a lot of scenarios, and therefore you're taking it to be true because you believe that you've done enough kind of testing to show that it does actually work in all scenarios. All right, counterexample. So basically a counterexample is if you have a conjecture that you believe is true, if you can provide one counterexample that shows that it's not true, then the statement is false. So it's kind of like being able to prove a conjecture is false. So an example, I guess, that proves your conjecture is false. So what's nice is, when you do a conjecture, so why we can't say this is, a theorem or whatever, because we haven't proved it for every scenario, right? So you might test it and try it on 4 or 5 different examples and say, okay, I'm pretty confident that this is going to work, and so we're going to use this as my conjecture. However, you may not have thought of every scenario, right? And then someone comes along and says, well, what about this? And they provide you with a counterexample that then proves your conjecture is wrong. And so you only need one counterexample to be able to prove conjecture is wrong, whereas you need to be able to prove every possible scenario is correct to be able to have your conjecture count as like a theorem. All right, deductive reasoning. So deductive reasoning, we're going to talk about 2 different things today. We're going to talk about, so deductive reasoning uses laws of logic to form a logical argument. Basically, they're saying they're kind of looking at, what we can kind of already know to be true. Like we know some certain things or certain facts are going to be true. So we're using laws of logic and kind of using that as our basis to be able to prove our conjecture is true or false. All right, so kind of the rest of the stuff is just kind of going into a little bit more detail about what a conjecture is. I'm going to give you an example of one just so that you guys can have one. So like, for example, my conjecture might be, I might notice some stuff and I might say, okay, I'm looking at numbers and I'm looking at, I have a bunch of these numbers and I notice that every time I take an even number and divide it by 2, I get an even number. So like 40 divided by 2 is an even number, and 60 divided by 2 is an even number. And I'm like, wow, that must be my conjecture. I've proved 3 different statements here, right? So my conjecture would be, I would say my conjecture is an even number divided by 2 will result in an even answer. So that's my conjecture, because I performed 3 tests and I got my conjecture and it must be true, right? So a counterexample would then me to say, so this is my conjecture and I think it's true. A counterexample would say, well, what about 10? 10's an even number, and when I divide that by 2, I get 5. And 5 is definitely not an even number. So this is providing me with a counterexample to my conjecture that I thought was true. And so this is an example of a conjecture based off tests. This is an example of a counterexample that proves that my conjecture was indeed false. So then we talk about like the deductive reasoning, right? So I talked about like the laws of logic. So laws of logic have actually 2 different kinds of laws. It's called law of detachment and the law of syllogism. Some fun words here. So the law of detachment basically states that if a hypothesis of a true conditional statement is true, then the conclusion is also true. So if you have a conditional statement, remember, to review, a conditional statement is that if-then statement, right? So if the hypothesis, so that's the P part, of your conditional statement is true, then the conclusion has to be true. So remember, this is the one where we know the results, so we know the answer to my conditional statement is true, and we know the hypothesis is true. So that means that Q part has to be true. And that's just kind of using logic to formulate our response, right? So if we know that that has to work in every scenario. The law of syllogism here, which is kind of like, we're going to use this a lot when we get into proof writing here in the next, in a little bit. But the law of syllogism says, okay, follow this law. So if you have a hypothesis, then you have a conclusion. So in other words, if you have P, then you have Q. So now my next thing I said, well, if I have Q, well, then I have R. So if all of these things are true, if this is true and this is true, then our conclusion can say, okay, well then if P implies Q is true and Q implies R is true, then by the law of syllogism, doesn't it make sense that P implies R is also true? So you're basically kind of cutting out the middleman there. So you're saying P is true, P implies Q is true, Q implies R is true. So that means these 2 things have to be true because they kind of share Q in common. Put this in a way that kind of is more geometric. So let's say let's talk about quadrilateral. So we'll talk about if a figure is a square. Think about what you know about squares, right? Then it's classified as a rectangle. So is that a true sentence? If a figure is a square, then it's also a rectangle. And so that answer would be yes. So by definition, a square is technically under the umbrella of a rectangle. Because a rectangle just has to have its quadrilateral, it has 4 right angles, opposite sides are parallel, opposite sides are congruent. There's different kinds of rules about rectangles, all of which apply to a square. And so we know this one is true. So this is true. So then we can say, well, I have quadrilateral. Remember, quadrilateral just means a 4-sided figure. Quadrilateral ABCD is a square. So our conclusion we said, so basically what we're saying here is if I have P, a figure is a square, then I have Q, it's a rectangle. So now I said, well, here's ABCD is a square. So I'm saying that if I have P, then I imply Q. So now I'm saying, well, ABCD is a square. Can we make a logical conclusion? And the answer is yes. Then we can say quadrilateral ABCD is a rectangle because this is a true sentence. So our conclusion would be that quadrilateral ABCD is a rectangle. So we can say that we can classify that as a rectangle based off of our law of syllogism. All right, I'm going to go through a couple examples. I'm not going to go through all of these just because I want to save some for you guys to kind of get some extra practice with, and that way you can kind of ask. All right, so let's kind of talk about a couple of these. I just want you to kind of, it just says describe the pattern and then or draw the next two numbers or letters to figure. So I thought maybe I'd do this one because I figure 1 is fairly easy. 2 is actually pretty hard. I'd like you guys to see if you can figure that one out. And 4 is just different because it's a figure, right? So it's like a drawing numbers. So I'm going to go with number 3 because it has letters. So the first thing I did was I said, okay, well, what's the pattern here? So I have C, E, G, I, K. So again, I'm thinking, okay, letters, I'm thinking the alphabet. So if I said A, B, okay, well then I have C, then I have D, E, F, G, H, I, J, K. It kind of looks, if you know, that we're kind of starting with C and then skipping every other letter. We're skipping every letter. So I go from C, I don't use D. Then I have E and I don't use F, and so forth and so on. So then my conclusion would be that after K, so JK, I would have L would be the one I would skip. So then I would have M, and then N would be the one I would skip. So I would have O. So the two next terms would be M and O. So this is what we mean by kind of recognizing a pattern, and then we can write a conjecture. I'm not really sure what kind of conjecture we're going to write for that one, but luckily we don't have to necessarily do that for this one. All right, let's go through a couple more examples. So again, this is on page 4-3 of your student journal, and we're just going to go through a few more examples. So I'm going to help you with 5, 7, 9, and 11. So we're going to do one of every kind of section, and I'm going to save the other one for you guys to practice. So in the first one, it says, make and test a conjecture about the given quantity. So you may have a different conjecture than me, so that's okay. I just want you guys to be aware of that. So the first thing it says is the sum of negative integers. So I'm going to make a conjecture. So this is going to be my conjecture about what I want to think. What do I think about the sum of two negative integers? So let me think about this. So let me try something else. So if I add it says sum of two negative integers. So -3 and -7. So sum means to add. Obviously negative means it's a negative number. And an integer means that it's kind of like a whole number, right? So it's not like a decimal or a fraction. So if I add these together, I get -10. All right. What if I pick any two other integers? So these were kind of both odd. I'm going to pick one odd, one even. I'm just going to try a couple different scenarios. I get -17. The sum of two negative integers. All right, so I could say, let's try two. I got two odd, one even. Let's try two even. I get -14. All right, so what kind of conclusion can I make from this? Well, if I have a sum of two negative integers, what I know to be true, it looks like the sum of two negative integers will always be negative, is what I'm going to guess. So the sum of two negative integers, my conjecture is, so the sum of two negative integers, I'm going to abbreviate here because I'm lazy, is always positive. Oops, not positive. What am I doing? Is always negative. So that was my conjecture. The sum of two negative integers is always negative because I tested on a few different scenarios and I used a couple different types. Like I tried to do two even, two odd, one of each, just so I could kind of test out my conjecture. And I tried not to use just just numbers between 0 and -10. So I tried to get some variety in there just so I could see if my conjecture was indeed, worthy or, base test enough. All right, let's try number 7. So that was literally just writing a conjecture. Number 7 says, find a counterexample to show that the conjecture is false. So we already know that the conjecture is false. So this is not a true sentence. So if n is a rational number, so we got to remember what a rational number is, then n squared is always less than 9. So a rational number is something like, so basically it's like any number you can think of in the whole wide world, with the exception of imaginary numbers and the exception of numbers like pi or square root of 2. And the reason why those numbers are not rational numbers is because they're numbers that go on forever without a pattern. So anyway, if n is a rational number, then n squared is always less than n. Well, I'm going to say, well, what if n is 2? So n's a rational number. Is 2 a rational number? Yes. So is n squared always less than n? Well, n squared would be 4. Is 4 less than n, which is 2? No, it's not. So therefore, this is my counterexample. My rational number of 2 does not fit this scenario. So that would be an example of a counterexample that proved my conjecture false. All right, number 9 says, use the law of detachment to determine what you conclude from the given information if possible. All right, if a triangle has equal side lengths, then the interior angle measure is 60 degrees. So basically, if you remember what a law of detachment is that the conditional statement is true. So if a triangle has equal side lengths, then the interior angle measures are 60 degrees. That's true. So if I give you triangle ABC has equal side lengths, then because of the law of detachment, we can conclude that triangle ABC has 60 degree angles. All right, last one, number 11. So I'm going to do one from here. This one uses the law of syllogism. It says to write a new conditional statement that follows the pair of true statements, if possible. So you have to have kind of the order right. So if it does not rain, then I will walk to school. If I walk to school, then I wear my walking shoes. So if P, then Q. If Q, then R. So P implies Q, Q implies R. So again, if this is true and this is true, then we can conclude that P implies R. So we're saying that if it does not rain, then I will walk to school. So that's a true sentence, apparently. If I walk to school, then I will wear my walking shoes. So by law of syllogism, I can conclude that if it does not rain, because that's the P part, then I will wear my walking shoes. All right, so kind of like you're kind of taking out those two parts. Those are the parts that kind of overlap, right? So those are the two parts that I can kind of take out in this law of syllogism. And so then my final statement kind of looks like this. All right, so there's a lot of writing on this one, and I know it's pretty important that you kind of try some of this stuff just because it does get a little and gets turned around. So I encourage you to do the lessons on big ideas. And of course, you can do some of the extra problems that are on this extra practice that I didn't do, and then always come to class with questions. All right, see you guys later.